have Christina Goldschmidt, who will talk to us about a line-breaking construction of the stable trees.
So thank you very much to the organisers for the invitation. It's a huge pleasure to be back in Cambridge and also to have a blackboard to write on. So despite the fact that I have slides, most of this talk is going to be on the blackboard. So I want to start by introducing what I mean by a stable tree. So I want to start by taking a Galton-Watson branching process, and I want to take the situation where I have a critical offspring distribution. So my offspring distribution has precisely mean 1. So consider a Galton-Watson branching process. With a critical offspring distribution, which I'm going to write as pk. So in particular, that means that if I sum kpk, that's going to be precisely equal to 1. Okay, and I want to take this tree and condition it to have total progeny n. So that gives me a tree that has n vertices, which is the family tree of this Galton-Watson process. So let's write TGWN for the family tree associated. Okay, so the stable trees essentially describe the possible scaling limits of these trees, depending on various properties of the offspring distributions. Okay, so let's first take the case where the offspring distribution has a finite variance. Okay, so if, let's say, sigma squared, which is going to be, that's supposed to be a k, so the sum over k greater than or equal to 1 of k minus 1 squared pk, so that's the offspring variance. If that's finite, then so the well-known result of David Aldous is that if I rescale the edge lengths in my tree, so imagine taking this combinatorial tree and putting edge lengths of length 1 on n, 1 on root n, then if I take that tree, then I have convergence in distribution as n goes to infinity to some limit, and I need to put a scaling in front of it in order for this to be correct. So I want to have some limit t2 here as n goes to infinity. So this thing here is a scaled version of David Aldous' Brownian continuum random tree. Okay, so I'll talk a little in a moment about why I'm using a slightly unusual scaling here, but this is square root 2 times Aldous' Brownian continuum random tree. Okay, so in order to give you some idea of what this limit thing here is, let me show you some pictures. So I'm not going to describe very carefully what it is, because that's not the main purpose of this talk, but I'd like to at least give you some sort of feel for it. So what I've drawn here is supposed to be a continuous function, and it can be any continuous function you like, but I'd like you to imagine it as being a standard Brownian excursion. So a Brownian motion that you've conditioned to do something it does with probability 0, which is come straight away from 0, stay strictly positive until time 1, when it returns to 0. Okay, so I want to show you how to get a tree from such a function. So first imagine you've got a glue stick, and put glue all along the underside of the function, and then I'd like you to imagine squishing the two sides together, and whenever two parts that have glue on them meet, they stick together. So hopefully that should do something like this. Okay, so you can see that you get a tree. Okay, so let me sort of do that backwards, because I want to emphasize sort of an important feature of this construction, which is that local minima of the function are going to correspond to branch points in the tree. Okay? So we wanted to think about what happens if you do this to a rather complicated function. So here's a simulation of a standard Brownian excursion. I should say that the nice pictures here are all drawn by Igor Kolchemsky. So here's a standard Brownian excursion, and here's the tree that you get out of doing that gluing operation, okay, with a sort of reasonably nice planar embedding. Okay, so that's how to describe this limit tree here, the Brownian continuum random tree. Okay, so this is a scaling limit for quite a large class of random trees. So I've said here that it's the scaling limit for the Galton-Watson trees, but there are various other things that can either be cast into this framework or which are sufficiently close that you also get the same scaling limit. So it's universal in a rather strong sense. So I'd like to talk about a generalization of this Brownian continuum random tree. So let's think about the case where the offspring distribution no longer has finite variance. Okay, so if my pk, so my offspring distribution, is now something that looks asymptotically like k to the minus 1 minus alpha as k goes to infinity, where alpha is in the interval 1, 2, then I'm going to get different behavior. Okay, so this is not going to be the most general statement possible. The most general statement would be that the offspring distribution is in the domain of attraction of a stable law, but let's keep it simple for the moment. So if I've got this sort of scaling behavior for the offspring distribution, then if I take my Galton-Watson tree conditioned to have precisely n vertices, and I rescale now by 1 on n to the 1 minus 1 on alpha, then that converges in distribution, again, as n goes to infinity, to, well, let's say some constant c alpha times another one of these rather special looking trees, and this is going to be the alpha stable tree. Okay, so this is okay, so the alpha stable tree was introduced in a series of papers by Jean-François Le Gall, Yves Lejean, and Thomas Duquesne in varying degrees of different versions, if I can put it that way. And I'm afraid I'm not going to be very good about citing the right papers in the right places, but much of this work is due to people in this room. Okay, so let's have a quick look at what the alpha stable trees look like. Okay, so there's a way of setting them up as encoded by functions in the same way as we saw that the Brownian continuum random tree was encoded by a standard Brownian excursion. Now, unfortunately, the sort of function you need to take in order to encode the alpha stable tree is a rather more complicated thing. So it is derived in some sense from a spectrally positive alpha stable Lévy process, but I don't really want to go through the details of how you do that because I won't get to the rest of my talk. But suffice it to say that you have coding functions that look rather more interesting now. So one of the things that we saw with the standard Brownian excursion is almost surely you don't have repeated local minima. Okay, now these functions are rather different in that we do get repeated local minima, and those repeated local minima actually are going to correspond in some sense to jumps of the stable Lévy process that's somehow underlying this. Okay, so in fact here we're going to have local minima which are visited an infinity of times. Okay, so already that should be telling you that we're going to get a rather more interesting set of trees here in some sense. And here's a different selection of alpha stable trees. Okay, so you can see that when we've got a parameter which is very close to 1, we've got these hugely bushy bits of the tree. Okay, and they get slightly less bushy until we end up with the Brownian continuum random tree here. Anyway, so thank you to Igor for letting me use his pictures. Okay, so could I maybe get rid of the screen, please? Okay, so to link back to something that Bénédicte was saying this morning, so she talked about Hausdorff dimensions of various trees which were generalizing the Brownian continuum random tree. So the Hausdorff dimension of the alpha stable tree is known and is equal to alpha on alpha minus 1. Okay, that's a result which was proved by Benedict and Gregory-Neumont and simultaneously, or rather independently, by Duquesne-Legal. Okay, so these are trees which crop up in a variety of different settings as scaling limits of various discrete models of trees, but also concerning aspects of, say, random planar maps. Okay, so I want to say a little word about the formalism that we use here, which is that of these R trees, or real trees. Okay, so if you've not seen these before, let me just say a brief word about the setup. Okay, so the right way of thinking about this is a sort of metric space analogue of the discrete notion of a tree. So a tree is a connected acyclic graph, and we need to work out what the sort of right continuum notion of a connected acyclic graph is. Okay, so we're going to think of this as a metric space, let's say TD, such that for every pair of vertices, or every pair of points, x and y in T, there exists an isometry, let's say phi xy, which goes from the real interval 0 up to dxy into T, such that the point 0 maps to x and the point dxy maps to y, and the image of this whole segment here is the path, the unique injective path between x and y. Is the unique continuous injective path from x to y in T. Okay, so that's somehow the right metric space way to think of this notion of a connected acyclic graph. Okay, so a piece of abuse of notation, if you like, but I've actually already used it. I'm going to write A times T, if T is an R tree, to mean, well, I'm sort of suppressing my metric D, and I'm going to write that to mean the tree with its metric rescaled by a factor of A. Okay, so the alpha stable tree is naturally endowed with a measure, which is really the limit of the uniform measure on the original discrete tree. So if I take my Galton-Watson tree in the domain of, with offspring distribution in the domain of attraction of a stable law, and I put mass 1 on n on each of its vertices, and then I think about what happens to that that measure when I let n go to infinity, it becomes something which is concentrated on the leaves of this alpha stable tree and gives me a notion of a uniform measure on that tree. Okay, so it's naturally endowed with a uniform measure. So T alpha which is supported by the leaves of the tree. Okay, so that gives us a natural way to pick points in the tree. Okay. So I'd also like to remark that if you think about this coding by an excursion function that I haven't told you how to generate, and you think about picking a point uniformly on the interval 0, 1, and where that gets mapped to in the tree, then that's another way of generating a point picked according to this measure mu alpha. Okay, so I'd like to think about picking a collection of points according to this measure independently. So condition on the tree and its measure, and then pick a selection of points uniformly at random. So let's let x1, x2, and so on be leaves sampled independently. From T alpha according to mu alpha. Okay, so what I'm going to be interested in is the subtree of my stable tree, which is spanned by those points. Okay. So let T alpha n be the subtree of T alpha spanned by these points. And let me also say that my trees are naturally rooted because I've got a sort of 0 point for my excursion. So let me think of that as a root for the tree, and let me in fact take the subtree spanned by these points at x1 up to xn, say. So by the points x1 up to xn and the root. Okay, so that's going to give me a picture something like this. Okay, so here's my root. Here's, say, x1, x4, x2, x3, x5, and let's say x6. And then there's the rest of the tree sort of hanging off. Okay, and I'm not going to be able to draw much of it here, but I hope you see the picture. So I've picked out a sort of subtree. Let me put it in a different colour of my alpha stable tree. Okay, so if I take more and more points, I'm gradually filling out and seeing more and more of the tree. Okay, and in fact, I can characterize the distribution of this object here by the sequence of its so-called random finite dimensional distributions. So if I can describe these sort of subtrees spanned by a finite collection of points, then I can tell you what the distribution of this T alpha here is. Okay. So I can think of T alpha n as two things really. It's got a sort of combinatorial shape, and then it's got edge lengths. Okay, and I want to, throughout this talk, think of it in those two different sections, if I can put it that way. So T alpha n is composed of a tree shape, which I'm going to write with a Roman T alpha n. I hope that's clear from the back. Okay, so this is a rooted, unordered, unlabeled tree. And the collection of corresponding edge lengths. Okay, so these things are sufficient to characterize the distribution of T alpha. So let's say the laws of that are sufficient to specify or characterize the law of T alpha. And moreover, I can think of T alpha as, well, the union over n greater than or equal to 1, T alpha n, and I need to take, again, the metric space completion as Benedict did this morning. Okay, so what I'm going to aim to do for the rest of this talk is to give what I think is a nice description of these reduced trees here, so of these sort of trees spanned by uniformly picked points in the stable tree. Okay, so let me start by reminding you of David Aldis's line-breaking construction of the Brownian continuum random tree. This 1 on square root of 2 will become clear later, I hope, or at least the reason that I'm taking a slightly strange scaling of the CRT will become clear later. Okay, so I want to start with the positive half line, and I want to take an inhomogeneous point process, or Poisson process, of rate or intensity T dt. Okay, so my intensity of points is getting higher as I move towards the right. So my points are getting closer and closer together. Okay. So let's have this length being called S1, this being S2, S3, and so on. So the first thing I do is I take a line segment of length S1. I'm going to root it at one end. And then I'm going to attach at a uniform position along that line segment another line segment of length S2. Okay. Okay. And then I'm going to repeat recursively in the same way. So I'm going to take a line segment of length S3 and I'm going to attach it to a point chosen uniformly at random from the whole structure that I've created so far. Okay, so let's suppose it goes here, and so on and so forth. Okay, so start from T1, which is a line segment of length S1, and then given that we've constructed Tn minus 1, attach a line segment of length Sn to a uniform point on Tn minus 1 to obtain Tn. Okay, so the question with which we started this work was, is there an analogue of this construction for the alpha stable trees? Okay, and the answer is yes, otherwise I probably wouldn't be standing here talking to you about it. And the first clue that the answer is yes is that there is a construction of these tree shapes, which is due to Philippe Marchal, which was somehow suggestive that there should be an analogous construction in the general alpha case. Okay, so I'm going to start by telling you about Marchal's construction. Oh, I haven't really finished my sentence, sorry. What I get for pausing in the middle. Okay, so what I should have said here is that these trees Tn, these are describing for me the n finite dimensional distributions of the Brownian continuum random tree, and that that's sufficient to really specify the Brownian CRT. So let me say that the t ends I'm building here have the same distribution as random finite dimensional distributions of my Brownian continuum random tree. Okay, so now onward to Marshall's algorithm. Okay, so this is the construction of the tree shapes. So Roman T alpha n. Okay, so again I'm going to start from just a single edge. Okay, I'm now constructing a discrete tree, so I no longer have edge lengths, but I'm nonetheless going to root at one end of this tree. Okay. And let me put a tilde here for a reason that I will come back to. Okay, so now I want to behave differently when I have an edge and when I have a branch point. So I haven't yet created a branch point, but in a moment I will. So I'm going to assign edges weight alpha minus 1 and vertices weight d minus 1 minus alpha, where d is going to be the degree of a vertex. And this is going to be whenever I have a vertex of degree greater than or equal to 3. Okay, so I've started from a single edge, and the first thing I'm going to do is I'm going to, well, pick either a vertex or an edge with weight, with probability proportional to its weight. Now, for the moment, I only have an edge because my two vertices both have degree 1, so there's nothing else I can do. And I'm going to pick that edge, and I'm going to subdivide it in the middle and branch off it a new edge. So my t tilde 2 is going to be this tree here. Okay, so now I have a vertex of degree 3. There are going to be two possibilities for the next step. So I'm now going to pick an edge or a vertex with probability proportional to its weight. So pick an edge or a vertex with probability proportional to its weight. So if I pick an edge, I'm going to again do as I did here. I'm going to subdivide it into 2 and insert a new branching off edge. And if I pick a vertex, I'm simply going to add a new edge coming out of it. Okay, so if I picked an edge, subdivide into 2, and branch off a single edge. If, on the other hand, I pick a vertex, we simply add a new edge coming out of it. Okay. And this, it turns out... Sorry?
What was the left one?
Good. Sorry, Ranko. Okay, so this is giving a growing collection of discrete trees, which turn out to have the same distribution as these tree shapes of the reduced trees of the stable tree. It was a bit of a mouthful, so let me write that down. So in symbols, t tilde n for n greater than or equal to 1 is going to have the same distribution as the tree shapes of these reduced trees of the alpha stable tree. And I should remark that the alpha equals 2 case here was already known back in the 80s and is due to Rémy. And you'll notice that if I take alpha to be 2, I'm never actually going to create any vertices of degree more than 3, because precisely when I get a 3 here, this cancels to give me 0. And so the only weight that I ever have is on the edges. Okay, so this is precisely giving you Rémy's algorithm in the case alpha equals 2. Okay, so moreover, one can rescale this collection of trees here in order to get a scaling limit, and that scaling limit is the alpha stable tree. Okay. So this collection of trees, if I rescale them by a factor which is n to the 1 on alpha minus 1, then that converges almost surely to a version of the stable tree. Okay, so that's a result which in this form is due to Nicolas Curien and Benedictas after a series of convergence in probability, convergence in distribution sort of results. Okay, so the novelty of the work that I'm going to present is really that we're going to get an almost sure limit which is the alpha stable tree without doing any rescaling. I'm going to construct a growing sequence of real trees which are going to give me the stable tree in the limit. Okay. So before I can introduce the construction, I need to tell you about a distribution which I think is probably not familiar to most of you. And that's the generalized Mittag-Leffler distribution. Okay, so to tell you what this distribution is, I need to start from a stable law. So let me fix a parameter beta in 0, 1 for the moment, and I'm going to convert this into something involving alpha a little later on. So I'm going to let sigma beta be a stable random variable with Laplace transform given by, so e to the minus lambda sigma beta is exactly equal to e to the minus lambda to the beta for lambda greater than or equal to 0. Okay, and in some sense, the normalization of my stable trees that I've taken is to make sure that this is in exactly this nice form without extra constants. Okay, so a random variable M has generalized Mittag-Leffler distribution which I'm going to write ML beta theta. So when my beta has to be between 0 and 1 and my theta has to be, well, anything that's bigger than minus beta. If I can describe its distribution via the following recipe. So the expectation of a test function f applied to M is given by some normalizing constant times the expectation of sigma beta to the minus theta times f of sigma beta to the minus beta. So I've taken my stable random variable, I've taken the power minus beta of it, and then I've sort of size biased by a factor of sigma beta to the minus theta. Okay. So why is this thing called a generalized Mittag-Leffler random variable? Well, if you take the theta equals 0 case, then the moment generating function is precisely the Mittag-Leffler distribution, or the Mittag-Leffler function, and the generalized is, well, it's something simpler. Okay. So this is for suitable test functions f. Okay, so it's impossible to get any sense of what this is really doing just from that formula, but that's maybe the most concise way to present it. So this is a distribution which is characterized by its moments, and perhaps those give a better idea of what's going on, I don't know. So these are ratios of gamma functions, so they're quite nice to work with. Okay, so the kth moment of M can be described as this ratio of gamma functions for k greater than or equal to 1. And when it comes to proving distributional results for these things, that's enormously handy. Okay, so there's one of these that you have met before. The beta equals a half case, which in a moment is going to correspond to everything that has to do with the Brownian continuum random tree. I've got that Mittag-Leffler a half n minus a half is the same as 2 times the square root of a gamma distribution, a gamma n1. Okay. So that hopefully is something recognizable at least. Okay, so where do these generalized Mittag-Leffler random variables come up? Well, as limits in certain Earn processes. So let me just say a little word about that. Okay, so suppose I've got an Earn scheme with 2 colours, let's say black and white. Okay, and this Earn scheme is going to be asymmetric in the sense that if I pick black, then I'm only ever going to add to the black weight. But on the other hand, if I pick white, I'm going to have a certain amount of weight that I add to the white in the Earn, and also a certain amount of weight that I add to the black. Okay, so it's a sort of anti-symmetric or asymmetric Earn problem. Okay, so let's take a generalized polyar Earn. Two colours, black and white. I'm going to pick a colour proportional to the amount of colour that there is in an Earn, in the Earn. So pick proportional to colour, or pick a colour proportional to its weight. If black, add 1 on beta to the black weight. If white, on the other hand, add 1 on beta minus 1 to the black weight and 1 to the white weight. Okay, so beta was something in between 0 and 1, so 1 on beta is bigger than 1, so I've got some space here to have 1 minus beta minus 1 and 1 both be positive here. Okay, so I'm gradually increasing the weights of these 2 different colours. So if I take a particular starting condition, so if I start with 0 black and theta on beta white, then I can describe the almost sure limit of the white weight as a Mittag-Leffler random variable. Okay, so if I let yn be the white weight at step n, so then the result due to Janssen says that n to the minus beta yn converges almost surely as n goes to infinity to some limit w, and this w has the Mittag-Leffler beta theta distribution. Okay, so it's arising as an almost sure martingale limit in the context of an Earn model. Okay. Right, so I hope that from the description of Marshall's algorithm earlier on, you've got some sense that Earns might be coming up here. So I'm constantly picking edges with, or edges or vertices with probability proportional to a certain weight. And that's a sort of reinforcing sort of Earn kind of construction. Okay. Right. So I'm gradually getting in the direction of our construction. So the next ingredient that I need to tell you about is what's the analogue of Aldous' inhomogeneous Poisson point process for the general stable tree. Okay, and that's going to be a Markov chain in this setting. Okay, so I'm going to take a Markov chain Mn such that the marginal distributions of my Markov chain are Mittag-Leffler with parameters 1 minus 1 on alpha and n minus 1 on alpha. So remember that alpha is a parameter somewhere between 1 and 2, and so these are giving me parameters that fall into the alpha, the beta and theta categories that I had over there. So I've got the marginal distributions being Mittag-Leffler, and I can tell you, well, more easily the backward transition probabilities than the forward ones, so let me give you those. So backward transition from, let's say, Mn plus 1 to Mn is given by the following. So Mn is obtained from Mn plus 1 simply by multiplying by an independent beta random variable. So where beta is independent of Mn plus 1, and has a beta distribution with, well, let me give you the parameters, n plus 1 times alpha minus 2 divided by alpha minus 1 and 1 on alpha minus 1. Okay, so again, the exact parameters are not so important, but I want to kind of tell you about the structure here. So in particular, this Markov chain here, Mn, is an increasing process, okay, because I get from Mn plus 1 to Mn by multiplying by something which is between 0 and 1. Okay, so what I've told you isn't enough to tell you that such a thing exists, but I assure you it does. And here's one way to construct it. Okay, so take independent random variables beta 1, beta 2, and so on with these distributions here. So then I can find M1 as the limit as some parameter p goes to infinity of the following thing. So a constant factor times p to the 1 on alpha times the product of the first p minus 1 of my betas. Okay, so I'm taking a product of beta random variables and I'm multiplying by exactly the right thing to sort of balance out the fact that these things are getting smaller and smaller and smaller. And this thing is essentially a martingale. It's not quite a martingale, but it's sort of asymptotically equivalent to a martingale. This almost sure limit can be shown to exist by a martingale argument. Okay, and then I can take my Mn simply to be M1 divided by beta 1, beta 2, up to beta n minus 1. Okay, and as long as you're willing to accept that this almost sure limit here exists, then that gives me a nice construction of this Markov chain Mn. Okay, so I claimed that this Markov chain here was somehow going to give me the analogue of the inhomogeneous Poisson point process. So I better tell you that that really is true. So a lemma that I think I'm not going to prove. If I take alpha to be 2, then these things are the ordered points of an inhomogeneous Poisson point process on R plus of intensity, well, a half TDT, because I've taken a different scaling. Okay. So these really are the points that I'm getting out of the inhomogeneous Poisson point process, so there's some hope that this is a generalization of Aldous' line breaking construction. Okay, so let me give you the construction. And let me also put an S there because there are actually 2 of them. Okay. So I'm going to start in exactly the same way as we did for the Brownian case by simply starting with a closed line segment rooted at one end, and its length is simply going to be M1. Okay. So throughout this construction, I'm going to use Ln to be the length of the sort of nth tree in my process. And so in particular, L1 is simply going to be equal to M1. Okay. So for n greater than or equal to 2, given that I've already constructed a tree Tn, construct Tn plus 1 as follows. Okay, so the first thing I'm going to do is generate yet another beta random variable. So let Bn plus 1 be beta with parameters 1 and 2 minus alpha over alpha minus 1, independent of everything else. Okay, so I'm going to take the next increment of my Markov chain, and I'm going to attach this proportion of that next increment as a new length to my tree. Okay. So glue a new branch of length, so mn plus 1 minus mn times this bn plus 1 to create tn plus 1. Okay, and I have a choice of two different places or two different parts of the tree that I might attach to. So either I'm going to attach this new length somewhere along an edge, or I'm going to attach it to an existing vertex. Okay, so I need to tell you the probabilities of those two things occurring. Okay, so I'm going to do this in two different ways, sort of in parallel. So I'll do the sort of detailed version first, and then I'll tell you how one can do something slightly less detailed on the right-hand side of the board. Okay, so I'm going to select the set of edges of Tn with probability the length of the nth tree divided by mn, which was where my Markov chain had got to. Okay, so that's something that's between 0 and 1. Okay. Or the internal vertex B with probability, well, given by a weight I haven't yet defined, but I will soon, divided by mn. So I'm going to have vertex weights which will add up to 1 minus ln on mn. Okay, so this will account for all of the probability. Okay, so let me try and continue on the next board. Okay, so if I pick the edges, glue my new branch somewhere chosen uniformly at random, so according to the Lebesgue measure on the tree that I've already constructed. So glue the new branch to a position chosen according to the normalized Lebesgue measure. On Tn. Okay. If on the other hand I pick the vertex, then I'm just going to branch my new segment to that vertex. So I need to tell you what weight I give to the vertex that I've just created here. So add, or rather assign, weight, let's say, mn plus 1 minus mn times 1 minus bn plus 1 to the new internal vertex. Okay, so to have a quick picture, I've constructed some sort of tree already. I come along with my new edge, and I either pick the set of sort of edges here, or I pick one of these vertices. If I pick an edge, then I'm going to attach my new segment somewhere uniformly along the sort of skeleton of this object, and I'm going to assign this new vertex that I've created here, this weight here. So this is somehow the weight left over. So up the top I selected this beta proportion of the increment of my Markov chain, and I want the complement, so the remaining weight, to get put at this vertex here. So if I picked an internal vertex, so if I chose to glue my new branch here, then I'm going to do so, and I'm going to increment the weight at the vertex. Okay, so if an internal vertex V was chosen, glue the new branch there, and increase the weight. So WV by the same quantity. So Mn plus 1 minus Mn times 1 minus Vn plus 1. Okay, so that tells me how to increment this vertex weight. Okay, and then finally, we have that the length of the new tree is the length of the old tree plus Mn plus 1 minus Mn times this beta random variable. Okay, so that's sort of version 1 of the algorithm. And it turns out that we can do without these vertex weights. Okay, there's some sort of internal magic going on in this construction, whereby I can afford to just keep track of the vertex degrees. I don't need to hang on to all of this weight here. That somehow, or enough of that, is encoded in the vertex degrees for me to be just able to track those. So let me sort of give you version 2, which is select the set of edges with probability ln on mn and the set of vertices otherwise. Okay, so if edges do as before, except for the part where I created a new vertex weight, because I'm not going to care about vertex weights. So do as before, ignoring vertex weights. If, on the other hand, I pick the set of vertices, well, I'm simply going to pick a vertex at random with probability proportional to, well, its degree minus 1 minus alpha. Okay, and glue the new branch to that vertex. Okay, so that gives a complete description, as it turns out, of these reduced trees of the alpha stable tree. So I think it took me a long time to get through the setup, if I can put it that way. But I think the message I would like you to sort of take home is that once we've constructed this Markov chain, which is somehow playing the same role as the inhomogeneous Poisson point process in the line breaking construction of the CRT, we've really only got fairly simple kind of independent elements which are going into making up what we do at each step. And you'll notice that this beta random variable, which is telling me what proportion of the new length I'm actually going to attach somewhere in the tree, that's just the same distribution every single time. So this is really about, as I think, simple as one could hope for a tree where I'm going to have to inevitably either attach to a vertex or somewhere along a new edge. And I think that's a good place to stop. Thanks very much for your attention.
Questions? Yes. Alvin?
Properties of the stable tree that you can better see using your construction than other construction?
I think so. Certainly there are distributional facts concepts about lengths in the tree, which are certainly there in work of Jean-François and Thomas Duquesne, but which I think are much more easily visible somehow with this construction. One gets kind of nice decompositions into products of independent random variables, which I think has a certain power from the point of view of working with it. I think we probably haven't fully explored the possibilities of what one can get out of this construction, but I mean certainly the line breaking construction of the CRT has been enormously useful.
Other questions? Yes.
So I guess all this is construction you can get by looking at a random walk on the complete graph, and then this somehow generates the uniform spanning tree taking the limit. So can you think about your construction as also arising from a random walk on the complete graph with some weights on the vertices, and then the limit of this in some sense gives you your construction?
I don't know, is the honest answer to that question. Clearly that would be lovely if that were the case. I think, so we've got, it's not obvious to me that there's a Galton-Watson tree which is doing exactly that, but perhaps there's some other tree which could be shown to converge to the stable tree which comes out of that sort of construction. That's a very waffly answer, but it's a nice idea.
Any other questions? Okay, well, let's stop.
Thank you very much.